Hello everyone, and thank you for joining. My name is Laya. I am an undergraduate student researcher with the Plasma and Electrodynamics Research Lab at the Propulsion Research Center here at UAH. This summer, I had the opportunity to conduct a three-dimensional measurement of electron temperature and density in a split-ring resonator microplasma. The ultimate goal of this research is to better engineer a miniature ion thruster for small-scale space propulsion. To begin, I will discuss what a split-ring resonator is. A split-ring resonator, SRR for short, is a type of plasma generation device. The structure of the SRR can be seen in Figure 1, which shows an unpowered ring. The SRR shown here is about 1 by 1 inch in size. We manufacture the ring using a copper etching process similar to one used by artists to make highly detailed and highly defined copper artwork. In order to produce a plasma, the SRR must first be placed into a vacuum chamber. In our case, we filled this vacuum chamber with a very small amount of argon gas. When a microwave signal is applied to the ring, a plasma forms from the argon around a small gap that is cut into the SRR. The activated SRR and associated microplasma can be seen in Figure 2. It is called microplasma simply due to its rather small dimensions. This research measured two important properties of the argon microplasma. These were plasma density and electron temperature. Plasma density is a measure of how many ions are contained in a volume of space. Electron temperature is effectively the energy of a plasma. In order to measure these properties, a special measurement probe called the Langmuir probe is used. The probe itself performs a scan of current versus voltage and outputs the results into a graph. In order to become useful, it is helpful to convert this graph of points into a single known function. This is done using the four free-fitting parameter method of nonlinear regression. The equation for current as a function of voltage is then useful in the equations of the Dryvestine method to solve for plasma density and electron temperature. Keep in mind, this measurement is for a single physical location in the plasma. In order to get a sense of the plasma as a whole, this measurement was performed a total of 400 times in different locations of a 3D space. These locations were arranged into four two-dimensional layers above the SRR. These heights were chosen to be 0.1575 inches, 0.25 inches, 0.5 inches, and 1 inch. We expected higher change in the lower regions of data, and so that is why we have more measurement fidelity there. At each of these height levels, measurements were performed in a 10 by 10 grid measuring 0.9 inches by 0.9 inches. As an example, the results for the 2D grid at 0.5 inches in height are shown in Figures 3 and 4 of plasma density and electron temperature respectively. In the plasma density surface plot, the peak is located around the gap in the SRR where the plasma is created. Using the results of the scans at each height, we can make theoretical predictions for performance of an ion thruster if it was built with that height dimension in mind. In an ion thruster, a plasma generator creates a plasma, which is then extracted and accelerated with a layer of grids. The theoretical performance calculations are for a grid height of the selected measurement. The final results in Figure 5 clearly show that as height above the SRR increases, the expected thrust would decrease. This is mostly due to lower and lower densities as grid height increases. As a note, the thrust levels are exceptionally low since the SRR was only running at a fraction of its maximum power level. This is due to concerns about our test setup reliability. Interestingly, specific impulse, which is a measure of efficiency, seems to remain nearly the same at around 3,870 seconds. This can be seen in Figure 6, taking into account the scale on the vertical axis. Using this result, it can be concluded that the optimal grid height for design of a miniature ion thruster is as close to the SRR as is physically limited. For further research, these same measurements with variable power levels would be useful. Beyond that, a physical ion thruster could be designed with the new measurements. This would unlock thrust testing and plume diagnostics to be performed. Thank you for joining me for a further description on the SRR microplasma analysis research. I look forward to hearing any questions you may have and would be happy to answer them.